Alright, 2.5, implicit differentiation. So before we do that, let's do a little warm-up here with the chain rule. Go ahead and pause that and do that. You should be able to do that pretty quickly. The pausing of the notes is super important. So pause that. Okay, welcome back. So we're going to take this exponent down in front and subtract 1 from the exponent. Now we're going to multiply by the derivative of the inside, and this is a little bit tricky maybe, but the derivative of the inside is actually -1 right there. So our final answer is going to be -4 3 minus x cubed. Alright, so obviously I hope it's obvious. I specifically put that in there because that would trip people up probably. So we want to be careful about that. Okay, implicitly defined function is a function with multiple variables that is not solved for one of the variables. So normally we use explicitly defined functions. Normally we try to get everything into y equals whatever. So that's called explicit. When we have stuff mixed together on a side, that's called implicit. An example are conic sections. Circles, ellipses, hyperbolas are some examples where that stuff is mixed in. Okay? So implicit differentiation refers to taking the derivative when stuff is mixed together and not solved for one variable. Okay, so here are the steps. I think it's probably better just to show you a problem, and then after I show you the problem, if you want to come back and look at these steps, then you can do that. Now, on the side, one thing about notation here is that when we take the derivative of y equals x squared, a lot of times we just write y prime because that's less characters, but another symbol is dy dx. So we can say the derivative of y is dy dx. Now, when we take the derivative of this side, we all know about the power rule, bring the 2 down, subtract 1 from that. But what we haven't been putting is we're taking the derivative of this with respect to x. That's why this becomes dy dx. And over here, technically, we would get dx dx. But dx dx is 1, so we never write that down. If you think about all the times we've taken the derivative already, if we had to write dx dx on the end, that would be kind of cumbersome. So there is a dx dx, we just don't write it down. So let's try this out. So what you're going to do is you're going to look at each term and you're going to take the derivative with respect to x. So the first step, super easy. So the derivative of that is going to be 2x. All right. Now, this next part is a little bit trickier. So we want to be careful here. So first of all, that's a product. X times y. Those are both variables. So we need to take the derivative of that. Now, first of all, I'm going to just keep the negative on the outside. So I'm going to leave that alone, and I'm going to take the derivative of this. So I need to use the product rule. Hopefully we all know that pretty well. Take the derivative of the first thing, which would be, technically it would be dx dx, but I'm just going to say 1. So the derivative of the first thing times the second thing. So it's going to be 1 times y, plus, using the product rule, which we should all know, and then the first thing times the derivative of the second thing. Now here's where it gets a little, it's not a big deal, you just have to memorize what to do. If there's another variable, you're going to take the derivative, so that's going to be dy dx. Because normally the derivative of a variable would just be 1, but this is all being done with respect to x. Okay? And so that wraps up the product rule there. Now we're taking the derivative of this. That's going to be 2y. And then because it was a y instead of an x, we need to put dy dx. That's it. That's the only thing that's different in today's lesson. Every time you take a derivative of y, you have to write dy dx. Okay? And this actually confuses students sometimes. That's a constant. The derivative of a constant is 0. So you want to make sure that you don't slip up on that. Okay? So now we're just going to do some work here. So this is going to be 2x. Distribute that. This is going to be minus y. Distribute that. This is going to be minus x dy dx. And here it's going to be 2y dy dx. All right. So I'm going to combine a couple steps at the same time here. So what I'm going to do is I'm going to be moving these to the other side. So I'm not going to worry about that. I'm going to flip-flop these. I'm going to put this first, and I'm going to put this second. I'm going to factor out a dy dx. So I'm going to factor out a dy dx, and I'm going to flip that around. So that's going to be 2y minus x. So think about that for a second. Make sure you understand that. If that's too many steps at a time, then don't skip that many steps. Okay, so I'm factoring out that dy dx, and I'm flip-flopping these two because I don't want that negative out in front. Then I'm taking these to the other side. So I'm going to add y to both sides, and I'm going to subtract 2x from both sides. All right? So that was about 3 steps at one time, but now I'm going to divide both sides by 2y minus x. And that would be dy dx. dy dx equals that. Now, it's important to realize, especially on a multiple choice test, if you look at the multiple choice selections and that's not an answer, then the first thing you should ask is, can I adjust this so that it matches one of the answers? Do I need to reduce? Do I need to do something? So hopefully you realize if we factor a -1 out of that, we could get 2x minus y. And if we factored a -1 of that, we could get x minus 2y. Threw me off for a second. So that's another way to write that, because if I divided a -1 out of here and a -1 out of here, then I could cancel those -1s and I would get that. So we want to be aware that we could write that answer in a different way. All right? So again, now the key here is this question says, so this says do both. All right, so we have to do both. I was excited for a second there. I thought we were going to be able to do less work because we're going to be evaluating at this point. But it says and. Okay. So I hope you can pause here, and I hope you can take the derivative of this implicitly after the one example that I've showed you how to do. So we have the product rule here, and we have the product rule here. So the derivative of x is 1. The derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. And since it was a y that I was taking the derivative of, I have to put dy dx. Okay? Now, this is going to be 8y cubed dy dx. And over here, that's the product rule again. So the derivative of that, derivative of the first thing, times the second thing, plus the first thing times the derivative of the second thing. Now you want to be careful here. The derivative of y is just 1, but it was a y, so you have to put dy dx. Okay? Now, if you didn't know what to do, I hope you could pause this now and finish the rest. The rest of this is just algebra. So, I can see that I have 3 terms with dy dx in them. So I'm going to subtract this over here, and I'm going to factor out dy dx at the same time. So if I divide this by dy dx, I have 2y, and this is going to be 8y cubed. And if I subtract this over here, that's going to be minus x squared. Okay, so all those together. Now on this side, I have 2xy, and I'm going to subtract this over here. All right? And so our last step on this first part of the question is to divide both sides by this. So dy dx is going to be, now I could factor a y out of the numerator, but it's not really that helpful, so I guess just for the sake of realizing it might be that way on a multiple choice test or something, we'd have that. And then this is being divided by both sides. All right. So that is finding dy dx. Then it says, and evaluate. All right? So that means we need to do something else. Now, if this question just said evaluate, then we would have gone from here directly down to here. And we wouldn't have done these steps. So I want to show it that way. So now, because we have simplified this down here, we could plug 2 and 1 in here and just get the answer. But I'm emphasizing to you that if it just said evaluate dy dx at this point, then we could have plugged our numbers in earlier. So if we plug 1 in for y 1 squared is 1 times 1, so that's going to be 1. And then I have x is 2, so 2 times 2 is 4, times y was 1, so 4, and then y, so that's 4y. Just kidding, that's 4 dy dx. So 2 times 2 times 1 is 4, and then I have dy dx right there. Okay, moving over here, plug a 1 in, 1 cubed is 1, times 8 is 8, so that's 8 dy dx. Okay, now here, 2 times 2 is 4, times 1, that's going to be 4. And finally down here, plug in 2 for x squared, 2 for x and then squared, so that's going to be 4 dy dx. All right, now if I start to gather this stuff together, then I would be subtracting 4 dy dx from both sides, and that would cancel. That's going to leave me with 8 dy dx, subtract 1. Be careful about being too clever and doing too many steps in your head and making a silly mistake. We don't want to throw any points away. If we get all the easy points, we can get a really good score. And then divide both sides by 8. So dy dx equals 3 over 8. Okay, so if the question just asked us to evaluate the derivative at this point, we could have just done that first step, and then we could have done this. If it asks us to find dy dx, then we have to do this. Okay? With respect to x, dy dx. Okay? Do not highlight stuff in orange. That's just for me. That just means I want that in italics, if I remember that. Okay, so outer function. So we have a chain rule here. So the outer function is sine, so the derivative of sine is cosine. Now we have to multiply that by the derivative of the inside. So the derivative of the inside, the derivative of x is 1, and the derivative of y is dy dx. The derivative of y with respect to x. Okay, and the derivative of x is 1, and the derivative of cosine is negative sine, and then because it has a y in it, that's going to be dy dx. Now, if we distribute this here, some of you might be hoping I was going to skip a step again there, but I didn't. All right. So I've got 2 dy dx's, so I'm going to add that to over here, and I'm going to factor out a dy dx. So that's going to be cosine x plus y plus sine y equals 1 minus cosine x plus y. And then I'm going to divide both sides by this. That's going to be cosine x plus y plus sine y. Technically, I should probably have this also. Okay. So this is just basically asking us to find dy dx. So if we take the derivative of sine is cosine. So we have the cosine of xy times the derivative of the inside. So that's a product rule. So that's going to be derivative of x is 1. So that's going to be 1 times y plus x times the derivative of y. The derivative of y is dy dx. Okay, using the product rule and the chain rule. So we're doing the chain rule first. Take the derivative of the outside, multiply it by the derivative of the inside. So this is the derivative of that. And then that is equal to 1, because the derivative of x equals 1. Okay, so if we distribute this, that's going to be y times the cosine of xy plus x times cosine dy dx equals 1. So it's going to be 1 minus y cosine xy, and then divided by so I want to be pretty careful here. That looks good. Sometimes it's a good idea to look around and see if there's something really similar to that, but maybe just missing a little bit. Okay. All right. So you have 4 of these on your assignment. I don't think it's worth doing 4 problems on this, but it's up to you. So my advice would be to do number 17 or 19 on page 142 and check your answer in the back of the book. And if you get it right, I would use my skips on the other 3 because they're kind of long. But it is up to you. All right. So what I would ask in class if you were here is, what is that? What's the graph of that? And hopefully you'd realize, well, it's not a circle, because if it was a circle, then the number in front of both of those would be the same. It's not a hyperbola, because then we'd be subtracting here. So what we're looking for is it's an ellipse. I don't know if you got to your conic sections last year or not, but that's an ellipse. And the normal format for that is actually to divide both sides by 36. So if we were to divide both sides by 36, probably could do that step in your head, but that would be 9. And then that kind of gives you an idea of what the graph looks like. The major axis is the square root of the center is off of h and k. So the center of this ellipse is 0, 0. The major axis is going to be x because this number is bigger. And we take the square root of that and we get 6. So it's plus and minus 6. So if you remember that, 1, 2, 3, 4, 5, 6. So that would be there. And 1, 2, 3, 4, 5, 6. That would be here. And then we take the square root of that. That's going to be 3. And because it's y, it's underneath the y. That's why I'm doing it on the y-axis here. Okay. Usually I'm not very good at drawing that. It's a little lopsided. Oops. That was pretty bad. Okay. So, there's the sketch of the graphs. I was supposed to graph them separately. So I will show that, though, as we go here. So what we're going to do is subtract x squared from both sides. And then we're going to divide by 4. So we're going to get y squared equals, we're going to split that up, so it's going to be 9 minus 1/4 x squared. And then we're going to take the square root of both sides. We're going to get the absolute value of y equals the square root of 9 minus 1/4 x squared. Okay, so we're going to get y1, and that would be the positive, so we have y, absolute value of y, so we would get plus and minus. So we're going to get that, and then I already kind of should have done this differently, so let me just do y2. That's going to be negative, and the negative should have been a little bit so that would have been down there. So I'm just going to color code that. I guess I could label them. So this is going to be y1 up here, and this is going to be y2 down here. Now, if you didn't have those memorized, you could do a little t-table, actually. So, but when you do that, you should think about what would be a good value to choose. So when you're looking at this equation right here, what would be a good number to choose for x? 0. Because then that would be the square root of 9, which would be 3. So if x equals 0, y1 equals 3. That's what we have right here. Now, the next thing you should choose is what would be another good number to choose for x? Well, how about 6? Because 6 squared is 36, and 36 over 4 is 9, and 9 minus 9 is 0. So if y is 6, x is 6, then y would be 0. And similarly, because that's x squared, negative 6, 0 would also work as well. So that's where those 3 points came from. Now, if we look at those same coordinates, but we plug them into y2 here, we'll get the same answers except we have this negative sign out in front. So that's going to be negative 3. This would still be 0. This would still be 0. So that would be this graph down here if we want to plot a couple points. All right. So now it says take the derivative of the explicit function. So what I want to do is I want to take dy dx. I put y1 because I'm just doing this equation y1. Alright? So what we want to think about there is that's to the 1/2 power. So if we take the derivative of that, that's going to be 1/2. And then we're going to have 9 minus 1/4 x squared to the negative 1/2. And then we're going to multiply by the derivative of the inside. So that's going to be negative 1/2 x. So now if we try to clean this up a little bit, this is going to drop down because of the negative exponent. So the only thing I'm going to have left in the numerator is negative x. And the denominator is going to be 4. And this is going to drop minus 9 minus 1/4 x squared. And if we take the derivative of the other side, if you think about it, if we're taking the derivative of this now, the only difference is that negative. So when I take the derivative of this, if I ignored that, I would get this, which you can't see right now. I don't know if you missed that whole thing or not. So when we took the derivative of this, we got this. When we take the derivative of that, if we ignore this, we would get the exact same thing down here. We just have it times negative 1. So if we multiply this times negative 1, that's just going to be a positive. Okay. Now, this says differentiate implicitly to show that the result is equivalent to part C. So what they're asking us to do is go back up here and just take the derivative of that with what we learned today. Okay? So, the first term was x squared. So if I take the derivative of x squared, that's with respect to x, that's going to be 2x. And the next term was 4y squared. So if I take the derivative of that, that's going to be 2 times 4, which is 8. And that's going to drop 1. But then I need to go dy dx. Shouldn't be that big of a deal. Anytime you take the derivative of y now, you got to put dy dx. And the derivative of 36 is just 0. So this looks pretty nice, actually. So subtract 2x from both sides. And then divide by 8y. So that's going to be negative 1/4 x over y, or negative x over 4y, either way. Now, y if you look at this up here, there's the negative x, and there's the 4, so that's all the same. So then we have y equals this. Now if you go back up here, that's what y equals. So this is equivalent, because, I don't know if we need to write it down again. Y is equal to this. So, if we plug that in there, then we get that. Okay, last one. Find the points at which a graph of the equation have vertical or horizontal tangent line. So, they said vertical first, so let's do vertical. Okay, so if we want a vertical tangent, that means we want dy dx to be dividing by 0. That's how you get a vertical tangent. So, if we want this to be 0, then that means we want 4y to equal 0. I don't need to worry about the numerator at all. I just need the denominator to be 0. That's going to happen when 4y equals 0, which happens when y equals 0. We have those two numbers on the chart. When y equals 0, that's going to be negative 6, 0, and positive 6, 0. If you want to look at the graph, negative 6, 0 is right here, and so that makes sense that there would be vertical tangent lines at those ends out there. I don't know if I didn't have this up there or not. Again. Okay, and a horizontal tangent line. So that's asking us dy dx equals, so we want that to be, the numerator to be 0. Okay, so if you look back here, for that to be 0, x has to be 0. So if we plug in 0 for x, back into the original function, that's probably important to say, when we got y equals 0, we're asking what points on the graph. So if we want to point on the graph, we have to go back to the original equation, or one of the original equations. So if you plug 0 into either of those, you get 6. We put denominator there and numerator. So if you go back in the original equation, if you're wondering where those came from, if we plug 0 back in the original equation for y, we get x squared plus 0 equals 36. So that's where the plus and the minus y came from, if you're wondering about that. Now here, if x equals 0, that's going to leave you with 4y squared equals 36, y squared equals 9, so y equals plus and minus 3. So there you go. Have a good day. Maybe a little 5 magic to finish off the lesson there. There you go. Alright. Oh, I guess I could have put it up here. It'd be even better.